Hello everybody and welcome back to another video in which I would like to speak about always at an introductory level to the scanning electron microscopy, which is SEM for short. These techniques uses an electron beams into the sample, and it collects the signals that are coming from the interaction between the electrons and the sample in a way that we're going to explain. And by mapping it into a screen, it is possible to create very beautiful pictures which you might have seen already, and they are like a picture, a photograph of the sample, in which one can tell, even without any knowledge about the way in which the signal is collected, the interaction, and the mechanism in general, but one is able to grasp some aspect from it because of the simplicity of the topography which is made, especially when related to the contrast. But let's go slowly. Let's start with the components of this system, which is essentially an electron gun. Okay, where the electrons are extracted actually from a filament, and we'll talk a little bit about this. And as soon as they are created, they go into an electron column with lens. There are different types of lens, which essentially the task is to reduce the spot size of the electron beam, and eventually they will hit the sample. Okay, once they hit the sample, electrons interact with the sample, and there are so-called backscattered electrons and other type of electrons that we will speak about. And those will be collected by Ehrenward Thorne detector, which can be positive or negative biased according to what we would like to do. And as soon as they are collected, there is a scintillator, a photomultiplier, and eventually is converted into a signal which is used in order to map, to raster and to map the image of the SEM eventually. So let's start from the way in which I would like to follow just talking maybe at the beginning about the components of the SEM. Then we will move on the type of modes, what parameters can be used, and eventually we'll talk about how the image is formed, and etc. and other things that whatever it comes to my mind, I will talk about. So the electron gun is essentially, we can picture it in our mind as uh, um, a filament. Okay, so this blue one is the filament. Filament historically is made by tungsten, which has been proved nice for the last 70 years. Some others can be lanthanum hexaboride or others. The main difference between these are essentially the cost and the life cycle. Tungsten tends to be a little bit to have a little less lifetime compared to lanthanum hexaboride and others, but this is what it is. This filament is connected with a bias. Okay. The bias, of course, has a resistance and this is negative, this is positive, of course. The filament work as a cathode, okay, and we will see in a second that there is also an anodic part, which is used to create an electric field. So there is a cage here, like this, okay. This cage is negative biased, whereas right below, for example here, we have the anodic part. So this is the, let's say, this is the cathode part, and this one is, okay, so it's clear that this is the positive part and this is the negative part, so another cathode. And the electrons are produced by a physical phenomenon which is called thermoionic emission, in a sense that the flux of electrons emitted by this thermoionic emission is proportional to a constant, the temperature squared, and e to the minus EW over kBT. Okay, of course kBT is the thermal energy, whereas EW it's the work function, which I would like you to remember as the energy that is needed in order to extract. So let's say this is the energy EW needed in order to extract from a metal, for example, an electron and put it into the vacuum. So of course, in order to reduce the consumption of this filament, the best will be to have one that works well when the temperature is low. So there is a thermoionic emission with low temperature and with a smaller working function, okay? So there is less energy needed in order to extract the electrons. So because of this anodic and cathodic part, we will have an electric field. And let me sketch, okay, this is all sketches, of course. I'm making the equipotential lines because of the electric field. So this will extract, okay, the beam. This is the picture for the electron beam, because this is the E, and we'll call this D naught, and let me fix a little bit the drawing. And this, we will call it alpha naught, for example. So it's important to characterize the beam having such angle and an intensity of the current and of current of electrons and the spot size, D naught. So in principle, what this, so imagine that this is the very tip of the filament. The effect of this, let me show it very quickly, this equipotential lines. So if we move it, let's say if, this is the 0, okay, and going up in this direction. So if we move it inside the tip, okay, they will extract the electrons, okay. So we kind of need to have a balance between, because if we go too much deeper, the beam size will be big, okay, and maybe you can think that this is a good thing, but actually it is not that good, because it means that if we have this spot size, we will need a lot of effort to be paid with the lenses in order to condense the beam, because eventually we will need to have a very the best will be to have a small spot size. Okay, so if the extraction is too much, we will need to work a lot with the lenses in order to converge the beam to make it smaller. Okay, so maybe it's worth to introduce directly what are the main parameters of the right at the beginning. Maybe it's more convenient to discuss about what are the parameters that are important for SEM. We already talked a little bit about the spot size. Okay, this is the sample. Down here we have the sample. And this is the beam size, okay? This is the beam, electron beam. dP is the spot size, the diameter of the beam of electron, and it's a very important parameter. We want it to be the smallest possible to increase the resolution of the image. There is the probe current, the current IP. Current is good because it's providing more electrons. More electrons means more details on the image, but the issue comes that they are mutually exclusive with the spot size. So if we increase the spot size, inevitably we will increase also the current, but increasing the current will not be beneficial for our imaging, because we need to find a proper balance between the two. For example, just to give you some numbers, a right balance will be a spot size of roughly 20 nanometers with an intensity of the probe current of something like 5 picoampere, something like that. That will be a nice balance between the two. There are other two parameters important. Okay, there is always an axle. We will call it optical axle. One is the convergence angle. We have divergence angle and convergence angle. The important one is the convergence angle, which discipline another parameter which is called the depth of focus that we will discuss later on. What you need to know now is that this alpha p, this angle needs to be the smallest possible, okay, in order to have the image very well at focus. And the last parameter is the voltage, the accelerating voltage of the system. So consider that we can say that the electrons are accelerated in the electron gun with an accelerating voltage that can go from let's say 0.1 to 30 kilo electron volt. Okay, this is roughly the voltage range, the energy range of which the SEM works. To each of these four parameters, to each one of these, this one, it corresponds a specific mode for running the SEM experiment. For example, the dP is known as a resolution mode. Okay, I anticipate already that this mode works with a small spot size, but not the smallest. It has to be like a balance between the spot size and the quantity of current. This is because of what we will see in a second. The probe current IP generates high current mode. Okay, in which we will again need a sufficient amount of current in order to overcome the contrast of the sample, and it comes out with a good quality image. And alpha p is a depth of focus mode. As anticipated, it has to be small as possible in order to keep the image at focus. And V is the low voltage mode. So if we keep the voltage below the 5 kilovolts, we will have pretty good information coming from the very surface of the sample. And whereas if the voltage goes from 5 to 30 kilovolt, then we will have information even from the deeper inside of the sample. We will often call the volume interaction, which is the interacting volume of the sample in which all the scattering event of the electrons occurs. Okay. Okay, so we discussed a little bit about the modes. Let's see what's happening into the electron column. No? So we have understood that there is schematically this aperture, okay, where we have the electron gun here. And this aperture is called D naught. So, okay, let's say it. Do it a little bit better. It's D naught. Okay. I anticipated that there are lenses, and the purpose of the lenses is to focus the beam and make it converging, reducing the spot size. And there are two important types of lens, at least two types of lenses. The first one is so-called condenser lenses. Okay, condenser lenses or lens. I don't know. I would say lenses. These lenses are located at a distance that we can call P, okay, from the aperture, and they have a depth or a height that we can call Q. Okay, so what's happening is we have what we call an optical axis. Okay, that goes all the way. It stays in the center, and from this, what's happening is something like that. Okay. Then they are because of the interaction with electromagnetic lenses, because these are electromagnetic lenses. We will have an effect which is the one of making the beam crossing the optical axis as a distance that we can call f, okay? In such a way that 1 over f is 1 over p plus 1 over q. We can also introduce P over Q, which is called demagnification. And on the contrary, Q over P is magnification, okay? Magnification. All right, maybe yes, we can discuss a little bit before continuing this to see what's happened below the column, electron column. Let's discuss a little bit about these condenser lenses, okay? So they are essentially, we can depict it as a metallic shield with an aperture, a pole piece. This is the pole piece. Inside this metallic element, there are a lot of wires. And we always have our optical axle. And of course, this is a symmetric on the other side. Okay, so 2, 4, 2, 4. Where, of course, in this case, the aperture is on the other side. It's here. Okay. So these wires will have a current crossing it, and this created by Biot-Savart law, a magnetic field. The F is, we will comment a little bit later about this equation, but effectively they are creating a magnetic field. Okay, I will just draw one part of this drawing, it's symmetric. And the magnetic field will have a radial component and a longitudinal component. Okay, let's call it B. This is B radial and B parallel. Okay, and it is understood that the electrons are coming from here, of course. Okay, and of course I will draw it on top where they don't need it. Okay. So what happens to the electrons that are crossing this magnetic field, okay? So just to be clear, this part that I'm drawing is what's happening here, okay? In this area. So the electron has been put into a magnetic field, external magnetic field. So it will experience, of course, a Lorentz force, okay? So the Lorentz force is proportional to the charge times B cross the magnetic field B. But essentially, the electron will first, as you can see from here, if you are putting your index into the direction of the electrons, okay, you will realize that in order to have a cross product, the first, it cannot interact with the longitudinal components of the magnetic field, otherwise this cross will be 0. So it has to interact first with the radial component of the magnetic field. It's a little bit difficult for me to show you. Maybe I can draw it. I can try to draw it. Of course, you will need to use the right-hand rule to understand where is the direction of these forces, and you are putting your index into the, let's give it a Z direction towards down. Then your middle finger goes as the radial, and your thumb, okay, is going outside from the screen, and it's telling you that as first the electrons, which has of course a certain velocity, a certain momentum, we will interact with the radial component of the magnetic B radial first, and the outcoming forces will be pointing outside from the screen towards your eyes. Okay, so as soon as the electron will feel these vertical forces coming out, you do the same. You put your index into the vertical components and your other finger towards, in this case, the parallel components of the magnetic field, and your thumb will tell you that the electrons will feel a forces that is pushing it radially, okay? Actually spiraling. It will be spiral and it will cross the optical axis in this point, in this precise point. So if you measure, okay, the distance between the first time that the electron interacts with the radial component of the magnetic field and the point in which crosses the optical axis, you will have this F, which is this F here that we draw earlier, okay? This one. Okay, so let's move on. We have introduced the magnification, okay, and the magnification. Both are important. And they are related as they are in the optical lenses of the distance between the source and the lens itself and the depth of the lens. Okay, let's introduce the other lenses, which are located maybe here. We call this objective lenses. There are different types of these lenses, pinhole, snorkeling, immersion, each of which has their own peculiarity, but I do not want to go into detail of that because I want to keep it introductory level. So the sample is down here. This is the sample, our beautiful sample. Of course, everything has to be put into the vacuum in order to avoid the interaction between the electrons and the gases that there are in the containers. So what's happening here is we have these objective lenses. These objective lenses are essentially their goal is to focus the beam into the sample, so it's a very important, delicate task. They can provide some further magnification, of course, but their task is to provide, let me put some prime, P2. Well, actually, this goes into the middle, and from the middle to here is Q2. Okay, again, we can introduce, let's say, P2 divided by Q2 as the second demagnification, whereas Q2 divided P2 is the magnification M2, and this is, let me call it 1, 1, 1, 1, 1, 1. Okay. So what's happened to our beam? We have an important as to say convergent angle, okay, like this, and a diverging. So you can tell that the one that's coming here, it's going proceeding, and this one proceeding, and this is all lost, all lost, and we can call it alpha the alpha diverging angle, whereas this one is the alpha converging angle that we need. And because of this aperture, there is the focus on the sample, and this is our final spot size. Okay, of course we will have this and this crossing, etc. Okay, but this is the point. Okay, so what can we talk about now? We can speak a bit about what are the type of what are the type of activities that a microscopist can do. So as an experimentalist, what you can do is essentially modifying 3 parameters. So you have, maybe let's talk about one thing first that I didn't mention. So, which is, we will come back later, but it's very important. What is actually this magnification? So this M, the magnification, is defined as the length of the cathodic ray tube, CRT, divided the length of the sample. But what is the cathodic ray tube? Okay, as I told you, the electron will interact with the sample. Electrons will have a scattering. We will speak about this, but the important part is that they will be backscattered. And as they are backscattered, we will place a nice detector which is producing a signal, and this signal will be used to map the topography of the sample and plot it into a screen. Okay, so this length is actually the length of the screen. So it's a digital display. We can think about we can think it about maybe 10 by 10 centimeter of actually screen. Okay, 10 centimeter by 10 centimeter, whereas the length of the sample is the length which we are considering in the sample. Okay, so the ratio of the two will be the magnification. Just to give you some number, as I anticipated, the cathodic is 10 centimeters, so it's 10 to the minus 2 meter, whereas the sample we can consider maybe 10 microns, so 10 to the 10 to the minus 6 meter, and this makes 10 to the 4. So this is 10,000 per magnification. So this is, but we will come back to this magnification. But now I forgot what I was saying. So the magnification we discussed. But I was going to say, oh yeah, there is an important parameter, which is actually a very important equation for this, and is called the brightness. The brightness is defined as the current of the probe divided by pi dp square over 4, so the area of the spot size, and pi alpha square, which is the solid angle, okay, in steradians. So this quantity is called brightness. Okay, it might not seem a big deal, but actually is super important, because this brightness is a quantity that is conserved throughout the column. So it's the same starting from the very electron gun all the way down until the very end. So it's a conserved quantity, very important relation. And from this you can tell that the parameters itself, in this case, these three parameters are linked to each other. And if one is changing, the other two needs to be adjusted in order to keep the brightness constant. So this is the important part. The brightness is constant throughout the column. If the microscopist change, as we will see in a second, one of these parameter, the other two inevitably needs to be modified in order to maintain the same brightness. Okay. If it were not for a phenomenon which is called aberration, we could consider that, let's reverse this equation, pi square dp square alpha square divided by 4. We could increase the current, increasing at the same time the convergence angle, but as anticipated, we want to keep this convergence angle lower, actually, not bigger. And if it were not for aberration, we could do that. But let's go back to what a microscopist can do. A microscopy can essentially modify three things, okay? Let's go from the bottom. The first thing that it can modify is the aperture of the objective lenses. So it can modify this aperture here, okay, this one here. This, let's call it a RAP. If increases the aperture, so if the aperture is increased, okay, what's happening is that we are increasing. If RAP is increasing, the convergence angle is also increasing. Okay, so we will not have a good performance in terms of depth of focus. We would like to have the aperture reduced to have a smaller spot size and a smaller alpha angle, which increases the depth of focus. The other parameter that a microscopy can change, besides the aperture, is also the working distance. What is the working distance? Working distance is actually this Q2 here, okay? So we can increase the distance from the sample to the lens, objective lenses. This will make a bigger spot size, okay, with more current. It will decrease the quality of the image. So we want to actually reduce if we reduce this Q2, we are increasing M2, which is the demagnification. So we are demagnifying more the spot size, and we are making better image. And we can also see from this relation here that if we are increasing the working distance, on the other hand, okay, if we increase it, we will have a smaller angle. So if dW is increasing, the angle is going down, and this will have an impact on the depth of focus, which will be it will be bigger, it will be stay more on focus, but we will come back to this. Another reason why we want to modify the aperture is also to limit this phenomena of the aberrations, which maybe we can discuss afterwards. Okay, so the last parameter which a microscopy can change is called the focal length. This F that I anticipate before, I spoke about before. The effect of this is to we can reduce the current that is crossing our coil. Okay, reducing this, we will increase the F. Okay, so by making the magnetic field weaker, we are essentially increasing F, and we are allowing more current to pass through. Okay, so it's another way of working on the SEM techniques. Maybe we can conclude this video here, and in the next video we will go deeply into the interaction between the electrons and the sample, and we will be discussing about aberration. We can discuss about the image formation, how actually the image is formed, and pixels and all this stuff, and the contrast as well. So thank you very much for watching, and we see you soon. Bye.